Welcome back, everybody. This is our second session in NEET previous year questions for chapter Wave Optics of class 12. Before this video, in this series, we have made one video and that video is available on our YouTube channel's playlist section. We have also started similar series for JEE previous years. So if some of your friends are preparing for those, then you can guide them through those videos. And if you find these videos helpful, then do press like button, share them and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, let's start today's video. In the previous one, we covered up to question number 13 and so. This was the last question which we covered. And today we will start with the next one. So here we have two slits in Young's double slit experiment having width ratio 1:25 and the ratio of intensity at the maxima and minimum in the interference is Ix by I min. So we have to calculate I max by I min. So we have a direct relation that I max by I minimum is equal to under root of I1 plus under root of I2 square divided by under root of I1 minus under root of I2 square. Now using this relation here, as per the given, we have I1 by I2 is equal to 1 by 25. So from this I2 is equal to 25 times of I1 or under root of I2 is equal to 5 under root I1. So substituting it here and we will get root I1 plus 5 root I1 divided by root I1 minus of 5 root I1 and whole square. This will give us 6 by minus of 4 square and that will give us 9 by 4 and that is option A. So option A is the right answer. Now let us move ahead. In the double slit experiment, two slits are 1 millimeter apart and the screen is placed 1 meter away. A monochromatic light of wavelength 500 nanometer is used. What will be the width of each slit for obtaining 10 maxima of double slit within the central maxima of single slit? So here we know that central maxima for single slit. So basically that is related to diffraction. And in diffraction, the width of central maxima in diffraction beta d, width of the central maxima is equal to 2 lambda times d by small d, and we have to make it equal to the width of 10. Where was it? Yes, here it is. We have to make it equal to the 10 maxima of double slit. Now double slit means interference, and in that beta is equal to lambda t by t. So here we know that it is given that beta d is equal to 10 times of beta of 2 lambda t, and sorry, it will be A here. For a single slit we have A, that is slit width, and it will be equal to 10 times lambda t by t. So lambda d is cancelled and this goes on 5. So from this value of A will be d by 5 and d is here 1 millimeter, so 1 by 5, so this will be 0.2 millimeter and that is option A. Let us move ahead. In the Young's double slit experiment, intensity of light at a point on the screen where path difference is lambda is k, lambda being the wavelength used. The intensity on the point where path difference is lambda by 4. So we know that assuming that if both of the slits are emitting light with equal intensity, then we have a relation that I is equal to 4 I naught cos square phi by 2, where phi is the phase difference, and phase difference phi is related as 2 pi by lambda times the path difference, where path difference is delta x. So initially our path difference is lambda and intensity is k. So if path difference is lambda, so phi lambda will be 2 pi by lambda into that is lambda, path difference is lambda, here it is. So phase difference will be 2 pi. So we can write that k is equal to 4 I naught cos square of 2 pi by 2, that will be pi. Now cos pi is minus 1, so basically from this we can write that k is equal to 4 I naught. Now we have to calculate intensity when it is lambda by 4. The path difference is lambda by 4. So path difference, oh sorry, phase difference when path difference is lambda by 4, that will be 2 pi by lambda into lambda by 4. So this will give us pi by 2. Now using again the same formula, so I will be equal to 4 I naught, that is equal to k. So k times cos square of pi by 2 by 2 means pi by 4. Now cos pi by 4 is cos 45, that will be 1 by root 2, and square of that will be half. So this is k by 2, and if we match it, that is option C for us. Now let us move ahead. In the Young's double slit experiment, slits are 2 mm apart and illuminated by photons of two wavelengths, lambda 1 and lambda 2. At what minimum distance from the common central fringe on the screen, 2 meter from the slit, will the bright fringe of one of the interference pattern coincide with the bright fringe of the other interference pattern? So suppose n1 fringes of lambda 1 are equal to n2 fringes of lambda 2. Now this distance of n1 fringes when wavelength is lambda 1 is equal to n1 times the fringe width, and so it will be n1 into fringe width, that will be lambda 1 d1 d by small d, because capital D and small d are same, equal to n2 lambda 2 capital D by small d. These both get cancelled. Now we can write that n1 by n2 is equal to n2 by lambda by 2 by lambda 1, and that will be 10,000 angstrom by 12,000, or basically 10 by 12 over 5 by 6. So we can say uh, fifth fringe of lambda 1 coincides with sixth fringe of lambda 2. So we have to basically calculate the distance from the center fringe. So let us calculate for the fifth fringe of the lambda 1. So let us calculate fifth fringe for the lambda 1. So that will be basically equal to 5 times lambda 1, that is 12,000 angstrom, into capital D, that is given to be 2 meter, and divided by small d, that is 2 mm. So minus 3. This gets cancelled. Here we will get 60. These three zeros are adjusted here. 10 raised to power minus 7, and this will further reduce to 10 raised to power minus 4, and that will be 6 mm. So that is option B for us. Option B is the answer here. Let us move to the next one. The periodic waves of intensity I1 and I2 passes through the region at the same time in the same direction. The sum of maximum and minimum intensities is. So we know that I max is equal to under root of I1 plus under root of I2 square, and I minimum is equal to under root I1 minus under root I2 square. If we add both of these, if we find out the sum, so what we will get? We will get I max plus I minimum, that will be twice of I1 plus I2, and that is option D. Now next one, a paper with 2 marks having separation D is held normal to the line of sight of observer at a distance of 50 meter. The diameter of the eye lens of the observer is 2 millimeter. Which of the following is the least value of D so that marks can be seen as separate? The mean wavelength of the visible light is 5000 angstrom. So here what we have to use, we have to find out, we have to use resolving power or limit of the resolving power. So for that we know that theta is equal to 1.22 lambda times t. This is the minimum value of theta which can be resolved. And here suppose this is the separation D in between the two holes, and we are observing from a distance of 50 meter. So here this theta will be should be equal to value of D by the this 50. So we can write it like, so here we will get D by 50, and this capital D is the diameter of the eye lens. This formula is related to the eye lens, and this is related to the this distance, this we can say separation and the distance. Here we have our eye. So from this value of D will be 50 into 1.22 into lambda, that is 5000 angstrom. 5000 into 10 to the power minus 10 divided by this diameter of the eye lens, that is 2 millimeter. So into 10 to the power minus 3. When we solve this, we will get 1.52 into 10 to the power minus 2, and that is basically 1.52 centimeter. And the nearest match will be option C here. Now let us move to the next one. Colors appear on a thin soap bubble, and the soap bubbles due to phenomena of. So we know that suppose this is a soap bulb. So the interface of a soap bubble is act as a thin film, and due to these thin films we have interference, and due to that interference we see the colors. So the right answer will be here option C. In the next one, in a Fresnel's bright prism experiment, the two positions of lens given separation between the slits is 16 centimeter and 9 centimeter respectively. What is the actual distance of separation? Now for the Fresnel prism, we know that D is equal to under root D1 and D2. So that will be under root of 16 and 9, and that is this will give us 4 into 3, that is 12 centimeter. So option B is right here. In the next one, interference was observed in interference chamber where air was present. Now the chamber is evacuated, and if same light is used with a careful observer will see. Now we know, as mentioned here, that there is interference happening. And for interference to happen, what is the criteria? That first of all, frequency should same, frequency must be same, and there must be a constant phase difference. Constant phase difference. Now, if we change the medium, frequency does not change and neither the phase difference. So, if interference was happening previously, so again interference will happen again. even the chamber is evacuated, or even the medium inside the chamber, or suppose type of air, suppose previously it was a we can say is carbon dioxide and now it is carbon monoxide or oxygen. So it does not matter that medium is changed or the whole system is evacuated. If frequency of the light stays same and phase difference stays constant, then there will be interference. So we can say option A is straightforwardly rejected. Now for a medium, lambda inside a medium is equal to lambda inside vacuum divided by the refractive index of the vacuum. Now, as mentioned here, that chamber is evacuated. So, if previously we had lambda m and now we have lambda v, and we know that lambda inside a vacuum is greater than the lambda inside a medium. So, wavelength is going to increase, and if wavelength increases, we know the fringe width, that is lambda d times lambda capital D by small d. So from this, beta is proportional to lambda. So if beta is proportional to lambda, means fringe width will increase. Fringe width increases as we evacuate the chamber. So here it is mentioned in option B that interference with brighter bands. Now this brightness of the bands is proportional to intensity, and nothing is mentioned regarding here that what we have done with the source, whether its intensity is increased or decreased. So we cannot say surely about B, and similarly for the C, that interference with dark bands. So we have no information regarding intensity, so we will reject both option A and B. And in option D, interference fringe with larger width. So and that we have already concluded that fringe width will be larger. So option D is going to be right answer. Now moving to the next one. In the Young's double slit experiment carried out with light of wavelength 5000 angstrom, the distance between the slit is 0.2 mm and screen is 200 cm from the slits. The center maxima at x is equal to 0. Third maxima, taking center maxima as 0th maxima, will be as equal to x. So we have to calculate third maxima distance, and that will be equal to 3 times beta from the central maxima, and that will be 3 times lambda t by t. So 3 and lambda is 5000 angstrom, and capital D is here 2 meter and small d is 0.2 mm, so 0.2 into 10 raised to power minus 3. So from this we will get 1.5 into 10 raised to power minus 2, and that will be 1.5 centimeter. Now here some additional information is also provided that central maxima is x is equal to 0. So whether we take center maxima at x is equal to 0 or x is equal to some random value, still suppose this is the central maxima, then there will be a first maxima, then there will be second maxima, and then there will be third maxima. Now this distance is equal to fringe width, so beta, this is again beta, and this is again beta. So whatever the value we take at suppose this is x is equal to, let's say, p, then this value, the third fringe will be at x p plus 3 times beta. So this difference between both of these will stay the same, that is 3 beta. So that's why we calculated 3 beta. Now moving to the next one. If the yellow light emitted by the sodium lamp in Young's double slit experiment is replaced by a monochromatic blue light of the same intensity, so we know that fringe width beta is equal to lambda d by small d. If setup is same, then beta is proportional to lambda. Now wavelength for red color is greater than the wavelength of blue color, so we can say from this that beta for the red color is greater than beta for the blue color. Now as per the question, that yellow light is replaced by the blue light. Now we also know that wavelength of the yellow color is greater than the wavelength of the blue color. And why? because blue color has the highest frequency. Blue color has the highest frequency, so its wavelength will be the lowest in the visible spectrum. So using this conclusion and using this relation, we can write that fringe width for the yellow color, beta for the yellow color, is greater than the beta for the blue color, and as yellow is replaced with the blue, so fringe width should decrease. So that is option A. So option A is right. Now in the next one, in Young's experiment, two coherent sources are placed 0.9 millimeter apart and fringes are observed 1 meter away. If it produces second dark fringe at a distance of 1 millimeter from the central fringe, the wavelength of monochromatic light used will be. So here, condition for a dark fringe is given by that path difference 2 is equal to 2n minus 1 into lambda by 2. This is the value of the path difference of the we can say darker fringe, and from this we can calculate the value of we can say displacement from the central fringe or distance from the central fringe. Just multiply it by capital D by lambda small d. So we can say here y will be equal to 2n minus 1 into lambda by 2 into capital D by small d, and this is given equal to here that is 1 millimeter. So that is basically 10 raised to the power minus 3. Now substitute the values. So here we have second dark fringe, so n is basically going to be 2, so 2 into 2 minus 1, that is 3. 3 by 2 into lambda we have to calculate. Capital D is here, I think capital D is, yes, here it is 1 meter away. So capital D is 1 divided by the small d, that is 0.9 mm. So 0.9 into 10 raised to the power minus 3 is equal to 10 raised to the power minus 3. Now when we solve this, we will get lambda is equal to 6 into 10 raised to the power minus 5 centimeter, and that is option D. For the next one, ratio of intensities of the two waves are given by 4:1. Then the ratio of the amplitudes of the two waves we have to find out. So we know here we have I1 by I2 is equal to 4:1. So we know that intensity is proportional to amplitude square. So we can write that A1 by A2 will be equal to under root I1 by I2 or I1 by I2 raised to power half, and that is mentioned to be 4:1 raised to power half, and that will be 2:1. That is option A for us. Now in the next one, the Young's double slit experiment is performed with the blue and green light of wavelength 4306 angstrom and 5460 angstrom respectively. If x is the distance of fourth maxima from the central one, then we have to find out a relation between them. So we know that fringe width is equal to lambda t by small d, and distance of the fourth fringe will be, that is the multiple of this. So we can say beta 4 will be equal to 4 times lambda d by small d. Now as we have different wavelengths, and we know that one is green and one is one is blue, this is blue and this is green. So we know that lambda for green color is going to be greater than the lambda for blue, and beta is directly proportional to lambda. Here capital D, small d and 4d are constant, so we can say that x for green is going to be greater than the x for the blue, and that is option C for us. Yeah, that's it. Because regarding option D, there some fringe number has to be equal, so we cannot conclude that for the fourth fringe that option D is going to be right. So only option C is going to be right here. Now for the next one, In the Young's double slit experiment, fringe width is found to be 0.4 millimeter if the whole apparatus is immersed in a refractive index of 1/4/3 without disturbing the geometrical arrangement. New fringe width will be. So we know that fringe width beta is equal to lambda capital D by small d, and if we immerse it into a water, so lambda changes and we can say beta inside water becomes lambda by mu into capital D by small d. Now we divide both of these, so we will get beta by beta w is equal to mu, and from this beta w is beta by mu, or basically lambda d by mu. So beta is here already mentioned, that is zero point 0.4. So 0.4 into 10 to the power minus 3 divided by 4 multiplied 3. So this will be 0.1. So this is 0.3 millimeter, and it is option A for us. Moving ahead, interference is possible with light waves, sound waves, both light and sound waves, and neither. So interference can happen both in transverse wave and longitudinal waves. So both light and sound waves. Option C is the right answer here. For the next one, the angular width for the center maxima in the Fraunhofer diffraction is 6000 angstrom. For 6000 angstrom is lambda naught. When the same slit is illuminated by another monochromatic light, angular width increases by 30%, the wavelength of the light used. So now width of the central maxima in diffraction is 2 lambda d by small d. Now to make angular, I can say, what is the angular width, we have to find an angle, and theta will be equal to y by capital D, and that will be 2 lambda by d. Now as mentioned here, so from this we can say theta is proportional to lambda. So initially theta node is proportional to 6000 angstrom, and after that it width decreases by 30%. So it decreases by 30%, so it becomes 70%. So we can say 70 by 100 of theta node is proportional to some value of lambda. Now what we can do, we can divide both of these and we will get 100 by 70 is equal to 6000 by lambda. So from this, this 0 get cancelled, and we can say lambda will be 4200 angstrom, and that is option B. So that is, I think this is one of the last one, and for this video we are ending it here. Again, hopefully this is helpful to you. If you have any doubts or suggestion, you can put them in comment section. I will try to resolve them. And also, if you like these videos helpful, then do press the like button, share them, and like to donate us, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.